All right, thank you all so much for coming today. Like Sean said, I'm going to be focusing on the generation of these calcite cap rocks that overlie Gulf Coast salt domes. So these calcite cap rock deposits are authigenic carbonates associated with native sulfur, and you can see these pictured here below. And the word authigenic here just means that the carbonates were formed directly where we presently find them today. And putting these deposits into a larger geologic context, you can see from this map here that there are actually many globally distributed occurrences of authigenic carbonates associated with elemental sulfur as well as evaporite deposits. And these are denoted in this map in yellow. But for the sake of this study, we're going to be focusing on this carbonate caprock that overlie these Jurassic Age salt domes in the Gulf Coast. And just to remind you again, the objective for this study is to determine the generation for this diagenetic caprock, which does remain relatively unknown. We're also going to be looking at today very similar deposits that occur in stratabound environments, but you can still see here that they contain very similar mineral phases. And these are from carbonates within the Permian Basin in West Texas. And just to give you guys a little bit of an idea of what the other globally distributed deposits look like, we also have similar carbonates from the Messinian strata in Sicily, similar deposits from the Permian salt domes in Germany, as well as the Triassic salt domes in Tunisia. And then switching gears just a little bit, I want to give everyone a good background information about the salt dome environment so that we're all on the same page. So the formation of a salt dome first begins with the formation of the evaporite layer from which it stems from. And our specific evaporite layer that we're going to be focusing on today is located within the Gulf of Mexico basin. And this basin is a passive margin rift basin that's located in the southeastern portion of the United States. And it started developing during the late Triassic period. And then in the basin, the salt layer began to form when an embayment along the proto-Gulf of Mexico allowed for this initial flooding of shallower portions of the basin with marine waters. And then over time, through multiple storm events, as well as this local subsidence within the basin, this led to the partial restriction of the basin from this open sea. And this led to the development of isolated seawater within the shallower portions of the basin. And due to this restriction and its partial separation, this led to the progressive evaporation of this seawater and the formation of this widespread salt deposit within the Middle Jurassic period. So this, over time, led to the accumulation of a really extensive, several kilometer thick salt sequence in the Gulf of Mexico basin that we know today as the Luan Salt. And then after the Middle Jurassic, and largely through the Cretaceous as well as the Paleogene, large volumes of sediment were deposited on top of this precipitated salt layer. So they were deposited as well as precipitated. And this large volume of sediment led to an increase in the overlying pressure that's acting upon this salt layer. And this pressure, as well as this sediment overloading, led to the formation of these salt domes within the Gulf of Mexico. So a salt dome forms when subsurface mobilized evaporites intrude vertically into surrounding rock. And so salt dome formation, or diapirism, occurs due to differential sediment loading on top of the salt bed, as well as salt having the two inherent characteristics of first, a relatively low density when compared to these overlying surrounding rocks, and then also salt has the ability to flow or deform when it's under really high pressures. So this allows for the vertical salt migration that we see in the Gulf of Mexico basin today. So this is a map showing the Gulf of Mexico salt environment. And these little white blobs here are the identified salt domes. And as you can see from this map, the salt deposit is very extensive. The salt domes are contained within the subsurface of the marine environment, and you can also see here that the salt domes are contained within the terrestrial environment as well. And these terrestrial domes are going to be the sampled sites for our study today. And then again, these domes stem from a mother salt bed that was deposited during the Middle Jurassic, and you can see the approximate boundary of this mother salt bed outlined in purple on this map. And this is a diagram showing a cross-section of a typical Gulf Coast salt dome. So these domes do vary a lot in thickness as well as height. Some of these domes are going to be really close to reaching the ground surface, like we see here in this picture, while others do remain buried at depths of around 5,000 meters. And as you can see from this 2-kilometer scale bar at the bottom, these things are very, very massive. And I also, in this diagram, I also just want to point out how this diapirism affects the overlying sediments. So the upward migration of this salt from its depositional location is going to cause a lot of deformation, specifically the upwarping and the onlapping of these overlying sediments, as well as it's also known to create these associated growth fault systems. The Gulf of Mexico is really well known for its large deposits of oil and gas stemming from these organic-rich Mesozoic source rocks. And so this upwarping and onlapping features, as well as the associated growth fault systems, really serve as these perfect traps for which these hydrocarbons to migrate to. In fact, in the Gulf of Mexico, the majority of the oil and gas are contained within these salt dome traps. So this is typically why we find these large local hydrocarbon sources developing along the flanks of these salt domes. So again, this is another map of the Gulf Coast with the salt diapirs as well as the Jurassic mother salt plotted. And also this time, I'm showing you these fault systems that are denoted here in red. And the majority of these faults that are contained within this Jurassic mother salt are likely growth faults that are related to the vertical migration of these salt diapirs. And these really extensive and abundant fault systems can serve as really excellent conduits by which hydrocarbons as well as groundwater can migrate through in this Gulf Coast environment. So another map of the Gulf of Mexico, this time showing the hydrocarbon distribution within this environment. So the green, red, and yellow all correspond here to different hydrocarbon phases, and you can see that hydrocarbons do have a large association with salt domes, specifically in regards to these domes located within the terrestrial environment. All right, so going back to this diagram just one last time, I also want to point out the two main components of a salt dome. So you have this rock salt stock, but then you also have this overlying cap rock sequence as well. So zooming in on this cap rock, you can see that the cap rock does form in distinctive layers, and it also forms in the sequence that's characteristic to the Gulf Coast. So directly over, typically you have this anhydrite cap rock that directly overlies this salt stock, and then you have this outer layer of calcite carbonate, which is pictured here in gray. And you have this on the outer edge of the cap rock, and it also has associated sulfur deposits with it as well. And these cap rocks are thought to form through complex microbial as well as hydrological interactions that occur as the salt migrates upwards. However, the specific reactions that are facilitating the precipitation of this calcite cap rock are still largely unknown. So again, that's going to be the focus of this study. So past research has supported that the hypothesized calcite cap rock formation mechanism first begins with the upward migration of the salt. So again, as this salt is going to rise upwards from its depositional location, we're going to see the accumulation of these perfect, or we're going to see the development of these perfect hydrocarbon traps and the accumulation of these hydrocarbon deposits located along the flanks of these salt domes. And these hydrocarbon deposits can either be in a gas or liquid form, so either methane or petroleum. And then over time, as these domes rise closer and closer to the surface, the shallower portions of these domes are going to begin to interact with these meteoric fluids. And the Jurassic mother salt is composed mainly of halite, but it does have some minor anhydrite impurities. But when these shallow portions of the dome are going to interact with these relatively fresh fluids, that's going to lead to the dissolution of the really soluble components of the Jurassic mother salt, so mainly halite. And that's going to leave behind the relatively less soluble components, so mainly anhydrite. So that's typically why we think we get the development of this anhydrite cap rock directly overlying the salt stock. And then through continued interaction with these fresh meteoric fluids, over time we're going to get the dissolution of this anhydrite cap rock. And so the dissolution of this anhydrite cap rock is going to lead to a ton of free calcium as well as free sulfate being released within the pore waters of the salt dome environment. Past research has also supported that some microbes can promote the production of dissolved inorganic carbon species through sulfate reduction. And through this process, the microbes use a hydrocarbon source, either petroleum or methane, as an electron donor by which to reduce this sulfate. And this reaction forms dissolved inorganic carbon species as well as hydrogen sulfide. And it's thought that these dissolved inorganic carbon species, which is typically either a carbonate or bicarbonate, can then combine with the free calcium in the system to promote the precipitation of this authigenic cap rock that we typically see overlying this anhydrite cap rock. But again, the specific natures of these reactions is still relatively unknown, specifically in regards to what specific hydrocarbon we're using, so either gas or liquid. And then also what specific redox reaction is actually promoting the production of this authigenic caprock. So that brings me to my study objectives, which were to determine the carbon sources for the caprock calcites, so whether this either be petroleum or methane, to also determine the specific microbial pathways that are promoting this authigenic carbonate, so whether that just be through sulfate reduction or possibly methane-dependent sulfate reduction, and then also to characterize what effect these redox reactions are going to have on the salt dome system as a whole. So luckily for us, insight into the diagenetic history of this caprock can be obtained through the use of carbon and sulfur isotopes. So to nail down the specific hydrocarbon source being used that's facilitating this precipitation of this authigenic caprock, we can use carbon isotope values of the caprock. So the carbon isotope values of this carbonate are going to depend directly upon the pool of dissolved inorganic carbon from which that carbonate precipitated. So by that I mean that there's going to be little to no isotope fractionation associated with these carbon isotopes, and the carbon isotopes of the carbonate is going to be essentially very similar to the carbon isotope composition of the dissolved inorganic carbon pool. Past research has supported that the salt dome calcite caprock carbon isotope value is very variable. So you can see here it ranges from about near neutral all the way down to -55 per mil. And it was first proposed that the carbon source for this caprock came solely from Gulf Coast crude oil. And crude oil, as well as organic matter in general, can promote the precipitation of this carbonate through the reduction of sulfate. However, you can see here that this Gulf Coast crude oil value is a relatively narrow range. It only ranges from about -28 to -23 per mil. So that doesn't really match up that well with our widely spread salt dome calcite caprock carbon isotope data, specifically in regards to our highly depleted carbon isotopes. So in the Gulf of Mexico, the only carbon source that's going to be abundant enough and also light enough in order to account for these depleted values is going to be methane. So methane has a carbon isotope value in the Gulf Coast ranging from -20 all the way down to -80, and methane is also known to promote the production of authigenic carbonates through this reaction here, which is the anaerobic oxidation of methane. So anaerobic oxidation of methane, or AOM, couples the reduction or the oxidation of this methane with the reduction of sulfate in order to produce this bicarbonate ion. And then in regards to our relatively heavy isotope values from our salt dome calcite caprock, these are likely stemming from the dissolution of the Gulf Coast marine carbonates. So you can see here that these have a carbon isotope value of about -5 to +5 per mil. And when these primary local marine carbonates are going to dissolve, it's going to shift the carbon isotope value of the dissolved inorganic pool to higher values. So therefore, likely these isotopically enriched values of the caprock are likely stemming from the dissolution of these Gulf Coast marine carbonates. And then we can also gain insight into the diagenetic history of this caprock through sulfur isotopes. And in contrast to carbon, sulfur isotopes are going to experience significant fractionation associated with different aspects of the sulfur cycle. And sulfur isotopes can be used as a proxy by which to identify sulfate reduction by looking at this characteristic fractionation that we see associated with that sulfate reduction in parts. So sulfate reduction in parts, what we call Rayleigh fractionation. And Rayleigh fractionation is this unidirectional kinetic isotopic enrichment of this sulfate that has undergone sulfate reduction. So on this graph here, on the x-axis we have the fractional amount of sulfur remaining within the system. On the y-axis we have the sulfur isotope value of the sulfate, and then we also have plotted in here the sulfur isotope value of the initial sulfur pool. But as you can see, as we move from left to right on this diagram, the amount of sulfate within the system gets reduced or gets decreased. And as the sulfate's getting decreased, we have the isotopic enrichment of this residual sulfate. And this is due to the kinetic isotope fractionation effect. And so then through microbial sulfate reduction, we also get the formation of this hydrogen sulfide. And you can see that in this diagram, as we move from right to left on this diagram, the fraction of the hydrogen sulfide is going to increase. And as this concentration of hydrogen sulfide increases, we get the actual progressive isotopic depletion of this sulfide, again due to the kinetic isotope fractionation effect. So in summary, sulfate reduction is going to show up in the isotopic record as an enrichment in this sulfate and a depletion in this hydrogen sulfide. And this Rayleigh fractionation shows up very nicely within our previously measured sulfur isotopes of the Gulf of Mexico cap rocks, which are pictured here. So you can see that the sulfur isotopes for all of these phases range from about -40 all the way up to +78 per mil. And this large range that's found within the salt dome cap rocks, again, is likely due to the large kinetic sulfur isotope fractionation effect associated with sulfate reduction. So the original input sulfate source for this system comes from the residual sulfate included within the Jurassic mother salt. And this has a really well-defined isotope value, about +15 per mil. So on this chart, you can see that we have the sulfides and elemental sulfur that are isotopically depleted when relative to the source sulfate. And then we have our major sulfates exhibiting enriched isotope values when in contrast to this original source sulfate for the system. So the Gulf of Mexico cap rocks really do perfectly exhibit this large kinetic sulfur isotope fractionation that's going to be associated with sulfate reduction. And this sulfate reduction likely occurs through either one of two pathways, either through the biodegradation of crude oil or possibly through the anaerobic oxidation of methane. So in order to meet our study objectives, we wanted to determine caprock carbon isotope values. We also looked at caprock carbonate associated sulfate sulfur isotope values. And carbonate associated sulfate, or CAS, is a trace sulfate that gets incorporated within the carbonate mineral crystal lattice upon carbonate precipitation. And CAS has been shown to accurately record the isotope composition of the pore waters concurrent to this carbonate precipitation, as well as preserve this signal very well within the carbonate rock record. And so this really serves as just an excellent proxy by which to identify sulfate reduction within the system. And also because both of these same proxies are coming from the same carbonate phase, it really gives us a way to directly link carbonate precipitation with sulfate reduction. We also wanted to examine the petrography and petrology of the samples in order to investigate the different mineral phases present, as well as look at aqueous fluid concentrations of modern Gulf Coast formation waters. And this was done in order to better investigate the important fluid-rock interactions that are hypothesized to play a role within the precipitation of this cap rock. So for this study, cap rock was sampled from 6 different domes. We have 5 onshore, which are Bowling Dome, Damon Mound, Hockley Dome, Davis Hill, and Winfield Dome. And then we also have 1 offshore Louisiana, which is Main Pass. And then also plotted in here are the specific locations for the sampled wells for the Gulf Coast formation waters. And these chemical compositions come from a paper from Crocker and Hanner in 2003 entitled Deep Fluids Within Sedimentary Basins. All right, so now I'm going to take you through our results. I'm first going to take you step by step through a plot showing our results for our carbon isotopes. And these results are going to be plotted against our 3 proposed carbon sources. So again, these are methane with the most depleted carbon isotope values. We also have crude oil, and then we also have a marine carbonate source. And for this plot, the closed circles are going to represent the carbon isotope values of the bulk samples. And the open circles are going to represent the carbon isotope values of our micro-drilled samples. So I grouped these isotopes by dome. So first we have the results from Bowling Dome, Davis Hill, Damon Mound, Hockley Dome, Main Pass, and Winfield Dome. So you can see that these carbon isotope results range from about -2 all the way down to -52 per mil. But you can also see that the vast majority of these results are falling below this -28 per mil. So this is going to indicate that methane is going to be the predominant source, the predominant carbon source that's leading to the precipitation of these carbonate cap rocks. We also looked at samples from the Permian Basin in West Texas. So if you remember, I showed a picture of these samples at the beginning of my talk. These are from, in contrast to the Gulf of Mexico, these are from a stratabound evaporite environment. But they still do exhibit genetic similarities with those rocks of the Gulf of Mexico cap rocks. So they serve as an interesting comparison here. And the Permian Basin has the same 3 proposed carbon sources as the Gulf of Mexico cap rocks. We have methane, crude oil, and also a marine carbonate source. And the two studied sites from the Permian Basin were Comanche Creek and Culberson. And so you can see these values range from about near neutral all the way down to highly depleted, so all the way down to -29 per mil. And this large range of values possibly suggests that these calcites are formed from a mixture of different carbon sources with associated differing carbon isotope values. However, these highly depleted values contained within the Permian Basin still do indicate that methane is also a likely source that's contributing to the formation of this authigenic carbonate. All right, and then I'm going to take you through our CAS results as well. I also just first want to remind you how sulfate reduction is going to show up within the isotopic record. Again, it's going to show up as this relative enrichment within this residual sulfate. So the source sulfate for the system is, again, this Jurassic mother salt with an isotope value of 15 per mil. And again, just like carbon, these results are also grouped by dome. So we have Bowling Dome, Damon Mound, Davis Hill, Hockley Dome, Main Pass, and Winfield Dome. So these CAS values range from about +12 all the way up to +70 per mil. But you can see that the vast majority of these domes are falling above this Jurassic mother salt, or enriched relative to this Jurassic mother salt. And sulfates that have undergone sulfate reduction have been shown to exhibit this characteristic fractionation. So therefore, these results do indicate that microbial sulfate reduction is occurring or has occurred in this environment, and this microbial sulfate reduction under closed system conditions. We also sampled CAS for the Permian Basin evaporites. In this environment, the starting sulfate comes from the Permian Basin evaporites, which is at 12 per mil. And the two sample sites, again, are Comanche Creek and Culberson. And both of these sampled yielded CAS values of +39.3. So again, significantly enriched when compared to the Permian Basin evaporites, and again, indicating microbial sulfate reduction under closed system conditions. And then when looking at our CAS values, plotted here in red, compared to some of our other sulfur isotopes in our previously measured, more studied domes, you can also see the presence of these depleted sulfide isotope values. So again, sulfate reduction, or sulfides that have undergone sulfate reduction have been shown to exhibit this depletion in the sulfur isotope value. So sulfate reduction here is going to explain these enriched CAS values, as well as these depleted hydrogen sulfide values. And then specifically when looking at Hockley Dome in this bottom right-hand corner, our CAS values aren't very enriched, or aren't really enriched at all relative to our source sulfate. And we believe that this is due to contamination of the Hockley samples with sulfide. So the Hockley Dome samples do contain a very large amount of sulfide, and it's been shown that samples that contain a lot of sulfide, it can lead to contamination as well as the overall lowering within this sulfur isotope value. And then from a petrographic standpoint, so the calcite caprocks are extremely heterogeneous. They exhibit really complex cross-cutting relationships through various mineral phases. And although the hand samples do vary extensively, they do all commonly contain a phase of carbonate as well as a phase of elemental sulfur. So zooming in on a specific sample of this caprock, we can see the commonly contained gray as well as white carbonate phase, and also these yellow elemental sulfur crystals. We also have some samples that exhibit this distinct banding. So you can see this banding of this finer gray calcite, which is separated in places by this white, coarser grained calcite. And these bands do vary in thickness from a couple millimeters to a few centimeters. And these bands are likely the result of the sequential dissolution of anhydrite and the subsequent precipitation of calcite. So again, just what I outlined within the hypothesized calcite caprock formation mechanism. Iron sulfides within these samples. So zooming in on a specific sample, you can see the presence of iron sulfides disseminated throughout the sample, as well as iron sulfides that locally line the cavities and fractures in some of the samples. And then when looking at these caprocks in thin section, they also exhibit the same same complex cross-cutting relationships. These thin sections have been stained with alizarin red. So the red phase in all of these samples is calcite. And I know these two look a little bit lighter than the rest, but they still have been stained with alizarin red. As you can see, from these thin sections, calcite does dominate the majority of the thin sections, just as it does in hand sample. And then when examining these thin sections a little closer in pairs, In these two pictures, we see the large presence of authigenic carbonate. Authigenic carbonate makes up on average about 60% of all of the thin sections that we've looked at. And we can also see the presence of multiple generations of this calcite. So on the left, you can see the two generations of calcite indicated by the difference in size as well as color. And then on the right, we see these defined zonations of the calcite phases. And these defined zonations were found in multiple samples, and they likely indicate the episodic growth of different calcite generations within this caprock. We also commonly see the replacement of sulfate minerals as well in thin section. So on the left, we see these anhydrite block pseudomorphs, and we see these anhydrite being replaced by this red calcium carbonate. And this is preserved in these abundant black sulfide minerals. And then on the right, we see this lenticular gypsum pseudomorph being replaced by barite. And then speaking of barite, we do see the large presence of barite in thin section. So in both of these photos, barite is this elongate white crystal, and it does seem to be associated with calcite as well as these black sulfide minerals. And previous research has suggested that barite forms relatively late within the paragenetic sequence of this caprock formation. This is possibly due to the sustained availability of dissolved sulfate, but also since barite is forming late, likely the isotopic composition of barite is not reflecting the environmental conditions that are the environmental conditions at the stage of carbonate precipitation. So this just really emphasizes the importance of our carbonate-associated sulfate isotope values. CS has been shown to accurately exhibit the exact same sulfur isotope composition of pore waters concurrent to this carbonate precipitation. We also looked at aqueous fluid concentrations of modern Gulf Coast formation fluids. We used FreeQC for this, and FreeQC is a web-based aqueous fluid modeling program. And we used this to explore the stability as well as the concentrations of certain minerals within the salt dome system. So we first looked at the saturation indices of salt dome-associated minerals. And the saturation indices just give insight into the likelihood of a mineral's precipitation or dissolution within the environment. And the saturation indice is calculated by taking the log of the IAP, which is the ionic activity product, divided by the KSP. And the KSP is the stoichiometric solubility product of that mineral. So if we're looking at a specific mineral, and the SI of that mineral is 0, that means the solution is in equilibrium with respect to that mineral. So the mineral is going to be dissolving and precipitating at the same rate, and we're not going to get any net dissolution or net precipitation from that mineral. If the saturation indice of that mineral is less than 0, that means the solution is undersaturated with respect to that mineral, likely indicating that we're going to be seeing the dissolution of that mineral. And then if the SI is greater than 0, then the solution is supersaturated, and we're likely going to be seeing the precipitation of that mineral. So this is a plot of the saturation indices, of a FreeQC generated saturation indices of salt dome associated minerals. We have the specific minerals here on the x-axis, and then we have the saturation indice on the y-axis. And then if you remember, anything above 0 is going to indicate the precipitation of that mineral, and anything below 0 is going to indicate the dissolution of that mineral. So saturation indices do indicate that aragonite, barite, calcite, and dolomite contain values greater than 0, and therefore we would likely expect them to precipitate in the Gulf Coast environment. And then on the other hand, we see negative saturation indices for anhydrite, gypsum, halite, and sulfur. So this is going to indicate that those mineral phases are unstable within the salt dome environment. And then when taking a closer look at this plot, just at the above 0 values, we can now clearly see, again, that aragonite, barite, calcite, and dolomite do contain positive saturation indices, and therefore we're going to expect them to be the dominant phases that are precipitating out within this modern Gulf of Mexico environment. But when we compare this modern model to our thin sections and the mineral distribution within our thin sections, they actually match up pretty nicely. In thin section, we see the presence of the supersaturated barite as well as calcite, and we also see the replacement of the unstable mineral phases, mainly anhydrite and gypsum. We also looked at, we also used FreeQC to look at the controls on the concentration of aqueous sulfate within the system. So past research have indicated that Gulf Coast formation waters do exhibit anomalously low sulfate conditions. So this is extremely different, I guess, unexpected, due to first, the large amount of sulfate contained within the Jurassic mother salt, and secondly, due to the high solubility of sulfate in the presence of significant sodium and chloride concentrations. And so it's been hypothesized that possibly this anomalously low sulfate concentration in the Gulf Coast formation waters are the result of several rate-controlled processes that are helping to keep this sulfate concentration low. And these hypothesized processes include dispersive fluid mixing, in which the dilution of the brines closer to the salt domes are going to be diluted due to the interaction and mixing with meteoric fluids. And this is because meteoric fluids typically contain little to no sulfate. Also, possibly through the dissolution of the sulfate and then the precipitation of this sulfate as barite. And then also possibly the removal of sulfate from the system through microbial sulfate reduction. So to first examine dispersive fluid mixing, it does seem possible that possibly this Gulf Coast groundwater could be mixing with the brines that are close to the salt domes. However, there was a study done by Crocker and Carruthers in 1986 that shows that these isotopic trends of the formation fluids, which are plotted here by these dashed lines, do not match up with the trends that are exhibited by the isotope compositions of these local groundwaters. So if the trend in formation fluids were closer to this trend of the meteoric waterline or intersected with this meteoric waterline, that would indicate mixing of the meteoric waters with the formation fluids. But we're not getting that. We're getting different trend lines, so that indicates that the formation fluids aren't meteoric in origin, nor do they indicate the mixing of meteoric waters with marine fluids. And then we also looked at the removal of sulfate from the system through the precipitation of sulfate as barite. And although barite is considered to be a late-stage forming mineral within the paragenetic sequence of the calcite caprock formation, there is some overlap of the sulfate isotope composition of barite and the anhydrite, the isotopic composition of the source sulfate contained within the Jurassic mother salt. So this possibly indicates a partial origin of barite from the dissolution of this sulfate. So the plot here is a frequency-generated model of the anhydrite dissolution and subsequent barite precipitation. So plotted here in blue is the amount of anhydrite that was dissolved into the system. In red is the amount of barite precipitated, and in green is the initial amount of barium contained within the formation fluids. And you can see that for all of these models, the amount of barium in the system, all of the amount of barium in the system is precipitated out as barite. But you can also see that the amount of anhydrite dissolved is much greater than the amount of barite precipitated. And we have seen that barite does occur in trace amounts within these salt dome thin sections. However, it's not really in sufficient enough amounts in order to account for these low sulfate concentrations on its own. So likely the removal of sulfate by barite precipitation is occurring within the system, but it's not really enough to account for these really anomalously low sulfate concentrations. And then we also hypothesized that microbial sulfate reduction could be leading to the removal of sulfate. So again, sulfate reduction is going to reduce the amount of sulfate within the system, and we already have evidence for microbial sulfate reduction within the system due to these enriched CAS isotope values relative to the source sulfate. So therefore, the removal of sulfate by microbial sulfate reduction could possibly be causing this low sulfate contents found within the formation fluids. So these results collectively indicate that the anaerobic oxidation of methane is the reaction that's responsible for this carbonate precipitation. And anaerobic oxidation of methane, or AOM, couples the oxidation of methane to the reduction of sulfate to form this bicarbonate ion. And this bicarbonate ion is going to increase the alkalinity concentrations within the environment that have been shown to lead to the production of authigenic carbonates. So looking back at some of our results with this now in mind, from a geochemical perspective, again, we have the carbon isotopes that indicate methane as their predominant source. We have the enriched CAS values that indicate microbial sulfate reduction under closed system conditions is occurring. And again, since both of these isotope proxies are coming from the same carbonate phase, this is going to indicate a direct link between the anaerobic oxidation of methane and carbonate precipitation within this system. So looking back at our results, this is a cross plot showing the carbon isotope values of the carbonates as well as the sulfur isotope values. And also plotted here is the lower limit of the Gulf of Mexico methane, which is -20 per mil. And then again plotted here is the Jurassic mother salt source sulfate, which is 15 per mil. Now any paired carbonate isotope value that's going to be below this methane, as well as above this source sulfate, is going to indicate that the anaerobic oxidation of methane was the formation mechanism that led to its precipitation. So you can see that from this diagram, all but 2 of the data points do indicate that the anaerobic oxidation of methane is occurring. And then looking at this same diagram just with a little bit more of a conservative approach, this time I set the cutoff for the Gulf of Mexico methane at negative 28 per mil. And this value is the lower limit of methane that excludes crude oil as a source. And you can still see here, though, that the majority of our data points are still contained within this anaerobic oxidation of methane range. And then from a petrological standpoint, we also have further evidence for AOM. So the anaerobic oxidation of methane forms these bicarbonate ions as well as these bisulfides. This bicarbonate ion can then combine with the free calcium in the system to form this calcium carbonate, as well as the bisulfide ion can then combine with the iron to form iron sulfides. And we see both the presence of authigenic carbonates as well as iron sulfides in our caprock deposits. So the anaerobic oxidation of methane interpreted here is very consistent with the distribution of mineral phases found within these samples as well. And then we also, when comparing this study to previous work done in similar geologic environments, first we're looking at a study by Ziegenbalg and authors in 2011 on these Stratabound deposits in Sicily. And although this is a different environmental deposit than the Gulf of Mexico, we still are getting these similar similar mineral distributions. We get the presence of evaporite minerals as well as authigenic carbonates and native sulfur. And so they used the same proxies that we did also to determine the generation mechanism for these authigenic carbonates. And they ended up with really similar results. Their carbon isotopes range from about negative 52 to negative 5 per mil, indicating methane as the predominant source. Their sulfur isotopes of carbonate-associated sulfate were very enriched, ranging from about positive 52 to positive 61 per mil. And they also interpreted that the carbonate generation mechanism occurring within these stratabound deposits was through the anaerobic oxidation of methane. And then we also took a look at studies done by Jaworska and Nowak on Zechstein salt diapirs. So these are salt diapirs that exist within Poland and northern Germany. And it became evident to us that some salt domes lack a carbonate caprock. So you can see here that these Zechstein salt diapirs only have this gypsum caprock overlying this salt stock. And they do in these studies report the presence of organic matter, but they don't report, or they lack local hydrocarbon sources, as well as they lack the presence of authigenic carbonates and elemental sulfur as well. But there are dissolved sulfur isotope values in the aquifers surrounding these Zechstein salt diapirs that exhibit sulfur isotope concentrations that indicate that closed system bacterial sulfate reduction is occurring. So this is a plot showing the sulfur isotopes of the sulfate on the y-axis as a function of this sulfate-chloride ratio. So this is similar to the Rayleigh curve, except from this time we're going from right to left as we're decreasing our sulfate contents, but we're still getting the enrichment in this sulfur isotope value. So groundwater that contains bacterially mediated sulfate is going to exhibit values along this trend line with this negative slope. As you can see from this study, there are several samples that fall within the slope of the bacterial sulfate reduction. And possibly this bacterial sulfate reduction is being coupled to the oxidation of organic matter, which is present, versus, or instead of, in the Gulf of Mexico environment where it's being precipitated by petroleum. However, again, despite this bacterial sulfate reduction, we're still not getting the presence of authigenic carbonates or elemental sulfur. So this could possibly imply that the anaerobic oxidation of methane and the presence of methane is necessary for these large deposits of authigenic carbonates. AOM increases both the dissolved inorganic carbon contents as well as increases the alkalinity concentrations. And these are both known to directly foster the precipitation of these authigenic carbonates. And we see the production of authigenic carbonates through the anaerobic oxidation of methane in modern environments as well, such as this deep ocean cold seep environment. So this is a seep site from on the western margin of Virginia. And this brownish green rock here in the foreground is this authigenic carbonate. And then these streams of bubbles back here is methane. And so in this environment, the sulfate being used is coming from the ocean. So this is different than the sulfate mineral that's being sourced from the Jurassic mother salt in the Gulf Coast environment. But again, we're still getting the same result, basically. We're still getting the precipitation of these extensive authigenic carbonate deposits. So this does further indicate the strong possibility that the presence of methane and subsequently the anaerobic oxidation of methane is necessary for these large-scale precipitation of these authigenic carbonates. And then looking back now at our revised hypothesized caprock formation mechanism and zooming in on this calcite precipitation step, we can now be confident in saying that the anaerobic oxidation of methane is what is leading to the production of this bicarbonate ion that's leading to the precipitation of this authigenic caprock. And looking at the broader implications of this study, we have both economic as well as environmental impacts. So from an economic standpoint, salt domes have been known to have a large association with deposits of natural gas and crude oil. And also, I've just shown that our carbonates or our caprocks produce economically viable minerals such as carbonate, sulfides, as well as elemental sulfur. And then from an environmental standpoint, the anaerobic oxidation of methane has also been considered to be a very important process that leads to the reduction of the emission of methanes within marine sediments. And mediating this methane efflux is especially important within this Gulf of Mexico environment, first because we know that natural methane is abundant here, and also because we know that there are extensive fault systems here associated with the salt diapirs. And so possibly these extensive fault systems could be serving as pathways for which methane as well as petroleum to escape to both the marine and the atmospheric environment as well. So possibly the anaerobic oxidation of methane occurring within these salt dome caprocks is helping to diminish the release of methane into the air in this Gulf Coast environment. So in conclusion, our carbon isotope values indicate that methane is the predominant carbon source for the precipitation of this caprock. Our sulfur isotope values imply that microbial sulfate under closed system conditions is occurring or has occurred here. The co-occurrence of both of these isotope values as well as our mineral distribution within this environment indicate that the sulfate-dependent anaerobic oxidation of methane is occurring. And this AOM likely leads to the precipitation of this authigenic caprock, as well as could possibly be helping to mediate the large release of methane from this Gulf Coast environment. All right, and then obviously didn't do this study alone. I had a really great sources of help for this project. I'd first like to thank Rich Kyle and Tim Lyons for their help, as well as Steve Bates and our own Michaela Adler for assistance with isotope analysis. I'd also like to thank our funding sources, which include CSUF, PRF, as well as a GSA graduate student grant. And then first and foremost, I would like to thank my advisor, Sean Lloyd. It's been such an awesome experience working with you for the past 2 years, and it's truly an honor to be your first grad student. I'd also like to thank the department as a whole, specifically my fellow graduate students. It's been so much fun getting to know you guys over the years. I wouldn't have survived without our office sessions. I'd also like to thank my family, who did not make it here for the defense, but they were out here for my graduation. They've been an awesome support system throughout my academic career. And last but definitely not least, I would like to thank these two, my partner Scott, as well as my adorable dog Winston. You guys have been an awesome support system throughout the past 3 years, and I definitely could not have done it without you two. And I'll take any questions.